In this video, we will review polar, cylindrical, and spherical coordinates. On this first page, we have all the important formulas we will be using. Once we've gone through these formulas, we will have a couple of examples, and then there will be 2 or 3 review problems for you to try. If we are given a point in 2 dimensions, we can notate that point as an xy coordinate, where we have our standard x-axis and our y-axis, and the x-coordinate tells us how far to the right we are along the x-axis, and the y-coordinate tells us how far up we've gone along the y-axis. But what we can also do is we can devise another coordinate system which will also specify this point. And it'll specify this point by saying how far we are from the origin, the radius from the origin, and also the angle we make with the x-axis. So that will be our polar coordinates. So we want to be able to convert from rectangular coordinates, xy, or Cartesian coordinates, to polar coordinates, r theta. And these are the formulas we use to do that. So to get the distance from the origin, we do a simple distance calculation. So it's x squared plus y squared square rooted. To get the angle theta, we can see from trigonometry that tangent of theta is going to be equal to y over x, which gives us theta is equal to the inverse tangent of y over x. And if we want to keep our theta between 0 and 2 pi, we can use our formulas over here. To go the other way, if we are given r and theta and we want to convert to these Cartesian coordinates, we can use these formulas here, also from trigonometry, because we can see that x, this distance x, is equal to r cosine theta, and the distance y, well, if we look at this, the sine of theta is equal to y over r, so y is going to be equal to r sine of theta. So polar coordinates were for 2 dimensions. Now, if we have 3 dimensions, we can use cylindrical coordinates, which is essentially just polar coordinates plus a height measurement z. So the idea in the graph, again, if we have this point x, y, z, we can imagine dropping this point, getting a line down from this point until it's onto the xy plane. Then from there, r is the measurement from the origin to this kind of projection down here. And then theta is the distance, again, the same as polar coordinates, from the x-coordinate, the x-axis to this r. So now if we have, and they're called cylindrical because polar is good for round things, so cylindrical, you have the round thing plus the height, so you have a cylinder. Anyway, so if you have something expressed in x, y, and z, and you want them in cylindrical coordinates, you find r and theta, just as you did in polar coordinates, and z is equal to z, so it's very easy, a natural extension. And if you have r, something in polar coordinates, r, theta, and z, and you want to convert to x, y, and z, it's the same as you had in polar coordinates. X is equal to r cosine theta, y is equal to r sine theta, and z is equal to z. Last, we have spherical coordinates, and like cylindrical coordinates, it's for 3 dimensions. So if you have a point x, y, z, we want to convert, basically what we want to convert is the distance from the origin, which now because we're in 3 dimensions, we call rho. And actually this should be rho, but sometimes I still refer to it as a radius. We still measure the angle from the x-axis, so that is our same measurement for theta as we had in polar coordinates. And then what we have, the third unit that we need is phi, and phi is the angle between the z-axis and our vector. So these 3 measurements, rho, theta, and phi, will determine a point uniquely in 3 space. To convert back and forth, if you have x, y, and z in Cartesian coordinates and you want to go to spherical coordinates, rho, again, it's just the distance from the origin, so that's going to be the square root of x squared plus y squared plus z squared. Theta, again, since it's the angle created with the x-axis, is the same theta that we had for polar coordinates. And now all we need to solve for is phi. And if we look at this diagram, we see that the cosine of phi is equal to adjacent, which is the z measurement, over the hypotenuse, which is rho, or r. In 3 dimensions, we call that rho. So phi is equal to inverse cosine of z over rho. If we have spherical coordinates and want to convert to Cartesian coordinates, x will be equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho cosine theta. The conversions back and forth are sort of the easy examples to do. The harder ones are when you want to express surfaces. We will have a couple of examples of those, and then the review problems will have a few more examples. We will start with an easy example of converting from one set of coordinates to another. So here we have rectangular coordinates, and we want to convert to spherical. And a second problem is to convert these spherical coordinates to Cartesian. So the first, convert to spherical, we have x equals 1, y equals -1, and z equals 1. So we plug that in to find rho, and you can see we have the 1 squared, the -1 squared, and the 1 squared, so that'll give us square root of 3. Theta, we have the inverse tangent of y over x. So here's our y, here's our x, and the inverse tangent of -1 is -pi/4. And then for phi, we are going to have the inverse cosine of z over p, or z over rho. So here we have z is our 1, and our rho is square root of 3. So our phi is approximately 57 degrees. Part B, we are given spherical coordinates, and we want to convert to Cartesian. So we will use these formulas here. So x will equal to rho cosine theta sine phi. So here's my rho, cosine theta, cosine theta sine phi. Y will equal to rho sine theta sine phi. So again, we have rho is 3, sine theta is sine of pi/6, sine phi is sine of pi/4. And then last we have z is equal to rho cosine theta. So rho is 3, and then cosine theta, cosine, this should be cosine phi, cosine pi/4. This next conversion is a little more involved. So the problem is to express the surface x equals 1, and also the surface x squared plus y squared minus z squared equals 1 in spherical coordinates. And I have our formulas here for reference. So the first surface, x times z equals 1. I just plug in for x over here, and for z over here, and I have it equal to 1. There's some trigonometric identities that give me a simplification. For my x squared y squared minus z squared equals 1, there was one thing I employed, which is to say that x squared plus y squared minus z squared is equal to x squared plus y squared plus z squared. And this is nice because we're in spherical coordinates. This gives us an equation of a sphere. So that was particularly good. And then, so in order to compensate, instead of doing just 1 minus z squared, I had to do minus 2z squared for this equality to hold. But once I have that, this equality, I'm going to plug it back into my original equation, and then I'm going to plug in my x, my y, and then my z, and then I also have to put in my minus 2z squared. So since I have my x squared, y squared, I just manipulated this for here because I know I have my cosine squared and my sine squared. I can group those together. That equals 1. So then I'm left with rho squared sine phi, and then I have my rho squared cosine phi minus my 2 rho squared cosine squared phi, just multiplying that out. So here again I have 1, and so, my sine squared and my cosine squared are going to give me 1, and I'm left with rho squared minus 2 rho squared cosine squared phi. Next, I have an example with the number of surfaces. So you want to graph and describe the surface expressed in polar coordinates, r is equal to a, cylindrical coordinates, r is equal to a, cylindrical coordinates, theta is equal to a being a constant on all of these, cylindrical coordinates, z equals r being the radius, this radius here, and cylindrical, z is equal to a constant a. We will start with the first one. So r is equal to a. In this case, r is fixed. The radius is fixed. So you may not, if you think about that, you may realize that this is a circle. And the other thing to notice is that theta, there's no restrictions put on theta, except theta goes from 0 to pi. So for every value of theta, so here we're at theta is equal to 0, we're going to be at r, whatever r is. And then at theta is equal to pi over 2, we're going to be at r. At theta is equal to pi, hopefully I drew this sort of circle correctly. This would be negative r. And then at theta, everywhere, at every value of theta, you have r. So essentially you have a circle. The second parameterization is cylindrical coordinates r is equal to a. So we know what r is equal to a looks like in the xy plane. So this is my circle in the xy plane. So you have to kind of use your imagination. Here's the z-axis coming out of the center of the circle. And then what we have is no restrictions on theta. Again, that's why we get the circle. And we have no restrictions on z. So you just imagine all these circles stacked up on top of each other, and infinitely many, so essentially what you get is a cylinder. The next one is in cylindrical coordinates, theta is equal to some constant a. So I did this kind of drawing in 2 dimensions in the xy plane because theta is in the xy plane. It's the angle between the x-axis and your vector, or your line. So here it is. I kind of translated it to the xy-z plane. But essentially, and even in the xyz plane, you're going from the x-axis and you're going across theta. And this is true for all r's. So, all these points satisfy the condition that theta is equal to a. And then the other thing you have is this line, basically all the points vertically up also satisfy this condition. So all the points that extend from z equals 0 out, because r, if we take negative values of r and go this way, then our theta becomes, it's a different theta. So really we just want from the z-axis out, from r equals 0 to infinity, and from z to infinity, we have this huge plane that satisfies the condition that theta is equal to some constant a. I am going to call this a half plane since it only extends out from the z-axis. And again, that's because if we go on the other side, negative r, then our theta is going to have to increase by 180. I had to move this over a little bit to make more space. So my next equation is cylindrical coordinates, z is equal to r. And what's helpful to notice is that z squared is equal to r squared, which is equal to x squared plus y squared. So essentially we have the form of a circle. So let's plug in some values for r and for z. So when z is equal to 0, r is equal to 0, and x squared plus y squared is equal to 0. So we have this circle of radius 0, so like this infinitely small circle. It's actually not even a circle, it's a point, and it's not even a point really. But anyway, we'll go on to z squared is equal to 4. So now we have x squared plus y squared is a circle of radius 2, and that's at height z is equal to 2. So somewhere maybe along here at z equals 2 we have a smaller circle. And then we look at z squared and r squared is equal to 9. So now we have x squared plus y squared giving us a little bit of a bigger circle as z gets a little bit higher. So what you see is we'll have this cone. As z gets higher, the circle gets bigger. So what you have is a cone with circular cross sections when the cross sections are taken, what would this be, horizontally. And last, we have cylindrical coordinates z equals a. At this point, there's no restriction on theta, so we can go 360 degrees around. There's no restrictions. And then there's no restrictions on r, so we go out into infinity in all directions. The only thing that's fixed is the z-coordinate is equal to a constant a, so you get this plane at z equals a. Now we have some graph and describe the surface, and these are spherical coordinates now. We have a is rho equals a constant, b is phi equals a constant, theta equals a constant, and rho equals 2a cosine phi. Rho equals a constant is essentially the 3-dimension equivalent in when you hold a radius r fixed in 2 dimensions, right? If you hold r fixed, you get a circle, and when you hold rho in 3 dimensions constant, you get a sphere. And the idea is that now you can have, because theta can vary between 0 and 2 pi, you go all the way around the circle, and then phi can vary between 0 and pi, so now you basically can go from here to here. The only restriction you have is that rho is constant, so you can go out far into space as long as you're equidistant or at a distant phi from this center. You can almost imagine having a dog tethered in space to the space station by this leash, and he can float around anywhere as long as he stays within rho, which is the length of his leash. Our next equation is phi equals a constant. So phi is the distance from the z-axis down, and so if we keep this constant and we let r vary in radius, so it can go from 0 to infinity, and also our theta can go from 0 to 2 pi, so we have to kind of be able to rotate this around. This goes around 2 pi. What we end up getting is this cone because we've rotated this line that's at an angle from z of phi. We've rotated this line around 360 degrees. Theta equals a constant in spherical coordinates is very similar to the cylindrical coordinates. So we have theta is our angle between the x-axis and our vector. The two things that are not restricted are rho. So rho can be very small, or our radius can go out into infinity. And now you have phi, the angle between the z-axis and your vector is also unrestricted, so it can be very shallow, except you do need to still be on the line of theta. Or phi can be a very large angle, but you still need to have your angle here be theta. What you get is the same half plane extending from the z-axis. This last surface, we are going to need some space, and it's mostly going to be algebraic. So rho is equal to 2a cosine phi. So the first thing we'll note is that theta can go from 0 to 2 pi. In other words, it's symmetric about the z-axis. The other thing we are going to notice is this is very similar to the z-coordinate equals rho cosine phi. In fact, if we multiply both sides by rho, we'll get rho squared is equal to 2a rho cosine phi. So we made it look a lot like z. We also know that rho squared is equal to, where is this? X squared plus y squared plus z squared. So rho squared is equal to x squared plus y squared plus z squared, which is equal to 2a, and then we plug in z here. And now you may see where we're going. This is starting to look something like a sphere. In fact, our goal is to make this look like a sphere. So we're going to move the minus 2az here. We're going to add a squared. That will allow us to complete the square here. But by adding the a squared on the left side, we need an a squared on the right side. And then I have my completing the square here. And what we have is an equation of a sphere with radius a, centered at 0, 0, and a. Those are my 4 surfaces for spherical coordinates for you. Now I have some problems for you to try, so you can pause the video, give them a try, and when you come back, I will have some solutions for you. Here are the solutions. And that's it for this video. Thank you for watching.